Awesome. Yeah, so my name is Erin Ernst, and I'm part of the geophysics team here at BGC. I've had the privilege of working with and learning from Eric Johnson since 2012 when since I joined this group. Eric Johnson is a senior geoscientist and developer with over 17 years of near-surface geophysics experience. He has developed numerous projects that streamline data processing and enhance data quality control. So the title of Eric's talk today is Automated Correlation of Geophysics and Borehole Lithology. This idea came, as many ideas do, from the feeling that there must be a better way to do this. So there must be a better way to get more value out of our geophysical data when we're making interpretations of geophysical data sets. There must be a better way to make these interpretations quantitative and representative of a given site. There must be a better way to gain a better understanding of how non-uniqueness is influencing our data set. There must be a better way to incorporate spatial trends into our interpretations. So we started out with a bit of a literature review, and there is work going on in this area, both across industry and academia, but nothing that exactly fit with the types of data sets and challenges that we were seeing. Also, based on this research and our wonderings, Eric began to build a custom Python-based tool about 1.5 years ago. And even as he started pulling the various pieces of this tool together, it became clear how valuable it was going to be, just starting from a basic data QC perspective. Since then, he's begun testing this tool using multiple data sets, and we have continually been impressed at how much more insight can be gained from the data that we've been collecting using this approach.
Yeah, thanks, Erin. So here I've just included a photo of myself collecting geophysics data at one of the hundreds and hundreds of sites that I've done geophysics surveys at. When you do something that much, you think about it a lot, and I often thought about how we have so much geophysics data, and we have all these boreholes. How can we better communicate everything the data is telling us? So briefly, what is geophysics? Geophysics techniques measures various phenomena like electricity, electromagnetic waves, gravity, and elastic waves. These phenomena are influenced by physical properties like resistivity, rock density, and seismic wave velocity. Geophysics uses imaging techniques that are similar to medical imaging techniques, though the medical techniques has the advantage of measuring across relatively small volumes. They often have access from different sides of the body, whereas geophysics surveys are typically run along the ground, and we measure tens to hundreds of meters into the ground. So going back to the seismic example, you can see us using a sledgehammer to generate seismic waves in the ground. We continue this survey along a linear array, and the results are a cross-section of seismic P-wave velocities, which are influenced by factors like the hardness of a material. In this section, the yellow colors are where seismic P-wave velocities are fastest, which coincides with a borehole log that logged bedrock at that depth. In this case, we're getting velocities of over 2,500 meters per second, whereas the blue colors represent slow P-wave velocities, which match where there is loose topsoil with velocities in the hundreds of meters per second. This is generally the traditional approach of correlating borehole logs with geophysics data. Another observation here is you can see that P-wave velocities at the top of bedrock is about 2,400 meters per second. So this adds to our confidence in interpreting the top of bedrock for the rest of the cross-section for that velocity. So there are known velocities for various material, but they do vary from site to site. For example, highly cemented limestone will have higher velocities than a lower cemented limestone. So we wanted a tool to better quantify these physical properties for the geology at a specific site, which can help improve our interpretation of our geophysics data. So how do we better quantify these physical properties for a specific site's geology? I mentioned the typical traditional approach, but there must be a better way, like this way. So I'll go over our automated approach with an example of seismic data in an environment with residual soils. Now, these residual soils typically occur in tropical environments where you get intense rainfalls and bedrock weathers in place. Under the Fuchs classification system, W1 is unweathered rock, and you find more and more weathered rock as you decrease depth. And W5 is completely weathered rock. So here's our sample approach. The first thing you need to decide is how far away do you want to correlate boreholes? So consider dipping geology and ground elevation differences between the geophysics lines and boreholes. For this example, we went with 30 meters. An interactive map is generated so you know exactly which boreholes have been found within 30 meters of geophysics data. And in this map, the green and gray circles have a radius of 30 meters, where the green circles indicate a borehole has been found within 30 meters of geophysics data. And the gray circles indicate where boreholes have no associated geophysics data. This way we know exactly which boreholes and which geophysics lines are included in the analysis. So for each borehole and for each interval of that borehole, we sample all the points within a set area. So again, another search parameter is defined. For this case, we are sampling 5 meters to the left and 5 meters to the right of where the borehole lands on the cross-section. The range and elevation for the sampled region is simply the borehole interval range. This is the result of the sampling process. The y-axis here is p-wave velocity, and the x-axis is categorical and has each interval type sampled. The type of plot we're looking at here is called a violin plot. Think of them as a histogram turned on its side, and a curve is fit to the histogram. So the widest bulge for each category is where the point density is greatest. And note that a point here refers to the median value of a sampled interval. As you can see in the example sampled interval, there are many p-wave velocities, but we just want one velocity associated with that interval, so we take the median. One trend that we can immediately see is that the more weathered rock is associated with slower p-wave velocities. So W5, which is completely weathered rock, has much slower velocities than W1, which is unweathered rock. And while it's useful to see the types of values associated with these weathering grades, some geotechnical designs require looking at geological context. So we developed a way to sample those specific regions too. Instead of sampling the interval, we are sampling at the contact. Again, we are sampling left and right by 5 meters, but also up and down by only 1 meter in each direction above and below the contact. These are the results of that sample. You can see now that we have a general reduction in p-wave velocities as we are no longer getting some of those deeper, faster velocities. This information can help interpret an entire cross-section by identifying where the most likely location is to find the top of each weathering grade. The peaks of each curve, i.e. where the bulge is the widest, represents the most likely velocity for that contact. So if we measure, say, 2,800 meters per second, it's most likely to be top of W1. And there's a chance that it's top of W1.5, but that's a lesser chance. And then there is no other velocities measured at that or no other categories measured at that velocity. So it's likely top of W1. So now that we know which velocities are most likely to be associated with which lithologies, or in this case, contacts, we can apply that knowledge to a brand new seismic survey, even if it has no boreholes on it at all, but it is the same site. This current view is p-wave velocities, with yellow as the fastest and dark blue as the slowest. Then we apply the algorithm to every velocity point in the cross-section, and we get this new plot where yellow is the most likely location to find top of residual soil. So that 100% here, which is yellow, correlates with the peak of those density curves we were just looking at. The dark blue indicates where it is unlikely to correlate with the top of residual soil here. And we get a cross-section with the most probable top of W5, W4, W3, W2, W1.5, W1. We now have a quantitative interpretation of the entire cross-section. Another way to visualize this in 3D is in 3D, where we are looking at the most likely location for the top at W3 across the entire site. This helps identify spatial trends in each contact across the site. And a quick second example I'd like to share is just another geophysical technique, electrical resistivity tomography, or ERT. Similar to seismic, we get a cross-section of data, but we get resistivity values instead. where resistivity is influenced by factors such as grain size, moisture content, and mineralogy. In this example section, we have a high resistivity values colored as yellow and low resistivity values colored as purples to blacks. So we expect finer grain material such as clays and silts in the darker part of this section. Also, like seismic, there are known values for various geological material, and they also range site to site. And here's the result of a sampling done using a few dozen boreholes and ERT sections. Instead of looking at residual bedrock, these are resistivity measurements collected in an area with lots of glacial sediments like sand, silt, and clay. The site also had organics like peat. These categories run along the y-axis, and the resistivity values run along the x-axis. When originally looking at the data set, I was curious about the overlap between the materials. So if there is additional information for each interval in a borehole log, it can be simply added to the analysis. Here, the lithology is the primary constituent, but it can also contain smaller amounts of other material. For example, most of the sand also had some silt. These points are colored green. Most of the silt also contained sand. These points are colored yellow. That helped explain why there was so much overlap between these categories. Also, in general, when there was some clay found in the silt, which are the blue dots, they were generally lower resistivity values for the silt category. Clays were found to have one of the lowest resistivity values recorded at the site, but still high resistivity, or still higher resistivity than we originally anticipated. Once we added this information, we found that all the clay intervals also contained silt, which explained why our values for clay were a bit higher than we'd expected. In summary, just having the program quickly plot boreholes along the data has been really helpful and something that we can do at night in the field or the next day in the office. We're getting more data insights into the specific site geology. We have better data QC. If there's an anomalous point, it becomes very obvious in these plots, and we can investigate, say, a seismic line that has a relatively slow velocities. Maybe there's a fault that helps explain that anomaly. Like the 3D view, it helps identify spatial trends, and it can be applied to historical data sets as a value add. Some of the next steps that we want to do are multi-parameter correlations. So we want to associate intervals with multiple geophysics types, like both seismic and ERT values at the same time. Also, the data is in a good format already, now that we've done these samples for machine learning, and that can potentially improve the probability sections even more. Thanks. And then I'll just go on to if there's any questions.
We do have a couple of minutes, Eric, and I see there's two questions in the chat. One says, one issue we often encounter is a lack of borehole data during the design of foundations and piles or deep shafts. Could this research help us provide more reliable information on soil profiles in areas where we don't have borehole data?
Yeah, another plan that we have for this is building a database of values. So say just clays. Any of these categories that we were just looking at, we'll have a database that grows and grows and grows of clays, and then we know that has silts, and we know the resistivity values and the seismic velocities for those values. And then we can look at a geology, even if it's a totally different site, we can kind of have an idea of why we expect clays to have these values. Even if we've measured it at a different site, we can combine the information, like lab measurements and these measurements here to apply that to a very new site. It's something that we do already anyway. When we go to a brand new site, we're already expecting a certain range of values for clay. And that's how we interpret data in sites with no boreholes. But now we can do it quantitatively and with more confidence with this method.
We've got a couple more here, Eric. The next one says, regarding your P-wave case study, do you have any issues with the different weathering grades not occurring in the expected monotonically increasing order? And if so, how do you deal with that scenario?
Right. If we're looking at the interval samples, we just left that in the sample data database. But when we were looking at the contacts, at the moment we just removed those. We identified them. They are flagged. If you're going from a weather in grade 4, then 3, then 4, like how do you define the top of W4 for that borehole log? At the moment, it's just flagged and removed, so it's just not included in the sample process.
And we're fortunate here. I think we have 2 more questions and we might even have time to tackle them both. The first one was, you mentioned machine learning as a next step. How do you see applying that?
With this one, this is something that could actually help with other sites. We've already started building a database across Africa with some of these samples. And what we want to do is just build various categories. So once we have, say, a certain weathering grade, we'll just keep accumulating ERT values for that, seismic values for that. With machine learning, you can just have more and more categories of data for a given like interval. And there's other information that we can include in that, say percent fines even. So I think it's a numerical, categorical machine learning is the type that we're looking at doing.
And we have one more I see in the chat here. Did you assess the differences between clays or between silts given the geochemistry of the soil?
We didn't take that information into account. I didn't have that available at the time, but it's something that what's really nice about this Python approach is that it's site specific. So any additional information that we do get like that can easily be added. I think the next thing I really wanted to add to that, if I can get my hands on, say, the saturated versus unsaturated, and then you can have that same plot colored just like it was, but have, say, different symbols for the saturated and unsaturated values. So you'd expect to see lower resistivity values for saturation. So anytime there's any information like that, we're happy to include it.
That's great. I think we do have time to answer any more questions. Folks can feel free to unmute themselves and ask. It looks like one came in here. Can you transfer this knowledge to predict subsurface stratigraphy based on only borehole information?
On only, yeah, well, I wonder how that would, I don't work in that field, I guess, when you're only working with borehole information. I guess because right now, the benefit of geophysics is that we are collecting data between the boreholes, and that's how we're able to connect the dots between boreholes. So trying to predict stratigraphy, I think you could, though. One thing in a way that one thing I've started doing is a bit of a cluster analysis for us to better understand the boreholes. And say the top of W3, if you get a certain depth of that, and you would have and that would be your sample. And across all your boreholes, you could build a histogram or like those violin plots. So you know the most likely depth for top of W3. And then, with machine learning, you could probably include information like hills and valleys and eastings and northings. So you'd already have an idea of where top of W3 is without geophysics data that way.
Great stuff. Well, it looks like we do have one more question. Feel free to unmute yourself there, Craig.
Thanks. Eric, one thing we've had to contend with when interpreting resistivity models like you is a high degree of uncertainty in the labels from geotechnical data. What one operator in the field might call clay might be, or a clay silt might be a silty sand. And also, there's a lot of subjectivity in that ground truth data. How do you think do you think there's anything in your method that helps alleviate this issue of subjectivity and fuzzy ground truth labels?
Right. Yeah. Thanks, Craig. I've definitely noticed that already. And the benefit I noted in the summary there of the data QC, it works both ways. So I think if there is an anomaly in one of those plots like clay, it's reading really high resistivity. We would go to that section and take a look and look at the resistivity. Is it maybe it's really deep and near the edge of our cross section, so there's just less data points in that area, or maybe we have a lot of points and we're really confident in it being clay based off the geophysics data, and then we should revisit that clay interval. So this is a good method for that too. I think it does QC the logs as well.